Welcome back. This is video 2 for lesson 3, Charles' Law for Unit 8 gases. This worksheet we're going to use as in-class example problems. This would be in your homework packet, not your original note packet that I gave you at the beginning of the school year. So all of these problems are going to use Charles' Law, which if you remember is V1 over T1 is equal to V2 over T2. All temperatures must be in Kelvin and the volume units have to be the same. So for number 1, if I look at this, the temperature inside my refrigerator is 4.0 degrees Celsius. If I place a balloon inside the fridge that initially had a temperature of 22 degrees Celsius and a volume of 0.50 liters, what will be the volume of the balloon after it fully cools in a refrigerator? So my initial conditions are right here. So V1 is 0.50 liters and T1 is 22 degrees Celsius. The new temperature is 4 degrees Celsius and I want my new volume. So there are my new conditions. So volume 2 is what we're looking for at our new temperature of 4 degrees Celsius. So both temperatures have to be in Kelvin. So when we do this, our first one we have to add 273 to 22. So 22 plus 273 is 295 Kelvin. And then our 4 degrees is 277 Kelvin. So we know that volume and temperature are directly related. So if the temperature goes down, our volume should also go down. So V1 over T1 is equal to V2 over T2. Now you can either cross multiply or we can multiply both sides by 277 Kelvin. That crosses this side out and crosses our kelvins out and we're left with liters. So 277 times 0.5 equals, divided by 295, hit equals, and we end up with this number. So with significant figures, we look at all of the significant figures up here. There's 2, 2, 2. So we should end up with 2 significant figures. So 0.47 liters is our answer. And it does go down. Number 2, a woman heats a balloon in the oven. If the balloon had an initial volume of 0.40 liters at 20.0 degrees Celsius, what will be the volume after she heats it to a temperature of 250 degrees Celsius? Hopefully the balloon is heat proof. So initial volume and temperature. What will be the volume with our new temperature? So V1 is 0.40 liters. T1 is 20.0 degrees Celsius, but we know we have to change that to Kelvin. So that is 293 Kelvin. We want to know what the new volume is if the temperature goes up to 250 degrees Celsius, which is 523 Kelvin. So let's put this in. V1 over T1 is equal to V2 over T2. So either cross multiply or we can multiply both sides by 523 Kelvin. That gets rid of that and leaves V2 by itself. Our Kelvins cross out. So we have to multiply 523 times 0.40, hit equals, divided by 293, and it gives us this value. Again, significant figures. It looks like 2 is our least number. So we end up with 0.71 liters. So the temperature went up, so the volume should go up, and it did from 0.4 to 0.71. Let's look at number 3. And this is something you might have noticed, you might not have noticed, but now you might look for it. On hot days, you might have noticed that potato chip bags seem to inflate even though they have not been opened. If you purchase a 250 milliliter bag of potato chips at 19 degrees Celsius and then you leave it in your car, which has a temperature inside of 60 degrees Celsius, what will be the new volume of the bag? And this can happen with balloons too. In the summer, if you buy balloons, let's say at Giant Eagle, and you put them in your car and you leave them in there for a while, they can explode because temperature inside of a car can really go up. So let's unpack this. So here is our original volume and original temperature. Here's our new temperature. We want the new volume. So the volume was 250 milliliters. Our temperature was 19 degrees Celsius, but we have to add 273. And we end up with 292 Kelvin. We want to know what the volume is at the temperature of 60 degrees Celsius. So that's 333 Kelvin. So if you'd like to pause the video and set this up and calculate what it is, this will be the time to do that. So if we look, V1 over T1 is equal to V2 over T2. So to get V2 by itself, we're going to multiply both sides by 333 Kelvin. That crosses that out and leaves us with V2. Our units of Kelvin cross out and we're left with milliliters. So 333 times 250 equals, divided by 292, and two significant figures, 60.0 and 250. So our volume is 285, but we have to reduce that down to significant figures, so 290 milliliters is our answer. Number 4, our last example problem. A soda bottle is flexible enough that the volume of the bottle can change even without opening it. If you have an empty soda bottle with a volume of 2.0 liters at room temperature, what will be the new volume of air if you place it in a freezer at negative 11 degrees Fahrenheit? So this one is a little bit more tricky because we have degrees Fahrenheit. So let's look at this. Here is our original volume and our original temperature. So V1 is going to be 2.0 liters. T1 is 25 degrees Celsius. So we'd add 273 to that, so 298 Kelvin. We want to know what is the new volume at negative 11 degrees Fahrenheit. So the first thing we have to do is change that to degrees Celsius and then to Kelvin. And that is degrees Celsius is 5/9 times the quantity degrees Fahrenheit minus 32. So be careful with this one. 5/9 negative 11 minus 32. So negative 11 minus 32 is negative 43 times 5 divided by 9 gives me negative 24 degrees Celsius. Then I have to add 273, and I get negative 24 plus 273 gives me 249 Kelvin. So there is my new temperature. So now I can put everything in here. V1 over T1 is equal to V2, which we are looking for, over 249 Kelvin. So I have to multiply both sides by 249 Kelvin. That crosses that out and leaves me with the new volume. So 249 times 2 divided by 298 gives me two significant figures, 1.7 liters. So the volume has gone down with the temperature going down.